We're today here for the Google Developer Summit session on GKE and Unity, a matchmaker made in heaven. I am Ishan Sharma, a senior product manager in Google Cloud, working in the Google Kubernetes Engine. What excites me most about my work is building a platform that powers some of the most successful games in the world. GKE, as we call it, is a managed environment for deploying, managing, and scaling containerized applications on the Google Cloud platform. GKE can be used to power a number of critical player-impacting game features. Today, in this talk, we will discuss how our partner, Unity, uses GKE to power its multiplayer matchmaker and how GKE can be used to scale these workloads to meet the demands of millions of players worldwide. With that, I will turn it over to Guillaume.
Hello, everyone. I'm Guillaume. Next slide. That's me. Engineering manager at Unity for the matchmaking service. Today, I'm here to talk about, like Ishan just explained, about our matchmaking service at Unity. So a couple items here. We're going to talk about Matchmaker and Unity gaming services. We'll deep dive a bit more into what is matchmaking exactly. Then talk about the architecture that we have, that we are using for our service and how we're using GKE for this. And then we'll talk briefly about what is next for the matchmaking service at Unity. So let's get going. So first of all, multiplayer games are extremely hard and extremely popular, among all kinds of gamers, casual gamers, core gamers, but also multiplayer games. Building multiplayer games is something that's really hard. Developers need to support a whole suite of services that will enable players to play their games. That's why with Unity services, Unity offers a whole suite of multiplayer services, which goal is to help creators to make those games without having to care about hosting or managing those services. We have game server hosting, lobby, netcode for game object, relay, voice and text chat with Vivox, as well as, of course, matchmaking. And others that are coming, that are out like very recently, like Friends, for example. So when we asked what are the most important features for our multiplayer games to players, here's what they're saying. They want to find a good match as fast as possible. They want to match with opponents and teammates of their skill level, and they also want to match with their friends. All of those are matchmaking concerns. That's why matchmaking is a centerpiece for a large number of multiplayer games. Resolving them is not easy, but Unity Matchmaker aims at solving those problems for game developers. So let's talk matchmaking and get a first understanding of what is matchmaking precisely. So the primary goal of Matchmaker is to group players and parties together in a match on a game server. Unity Matchmaker is tightly integrated with Unity game server hosting, so we will mostly be talking about bringing players together on a match that runs on a dedicated game server. So what does a matchmaking flow look like? The first thing that the player would do to join an online game is to create a matchmaking ticket through their game client and send it to the matchmaker. Then the matchmaker takes all the tickets that exist and tries to group them as well as possible together. And this is done following the matchmaking configuration that has been defined by the game developer. We will talk about that in details later in the presentation. Once a match is made, Matchmaker will request game server hosting to allocate a game server for that match. Matchmaker will provide information such as what is the build configuration that game server hosting is supposed to run for that match, what does the match that was made looks like, team and player composition, so that when the server starts, it has information about who are the players who are supposed to join and the distribution between the teams. Once the server is allocated, game server hosting provides information about the IP and port players are supposed to connect to. The information makes it back to the ticket that was created by the players. And as the player polls for the ticket status, once the information about the game server allocation is added to the ticket, player will know where to connect. Once they have that information, they can all connect directly to the game server that was allocated for them. And they're playing their game on a dedicated game server. So that looks pretty simple at first glance, right? Saving a matchmaking ticket, grouping player together, sending a request to allocate a server, save the information about the server, and return the information back to the players. But the reality is quite different. We're going to go through where we think it's so complicated to create a matchmaker service. So the most important thing is to properly segment your player population. The number of players that we try to match together has a direct impact on the time to match. A population too low, and the time to match increases. Because it takes time to find players to match. A population too high, on the contrary, it takes time to go through all the players that wants to play. For an effective matchmaking, we want to only try to put together players that can potentially be matched together. That's player population segmentation. Population can be segmented in different ways, like those examples we have here. Queues, like game modes, version of the games, or player characteristics. So how to make sure that the match that is created makes sense and that we are matching the right players together? First, we need to be able to define the composition of the match. How many players are in one match? How many teams? How many players in a team? Is it a 1v1 match? Is it a 60 players battle royale made of 30 teams of 2 players? Can the game start even if the match is not full? And we also need to provide a way for game developers to define more intricate rules, like making sure everyone has an equivalent skill level, making sure that everyone in the team is using a different character, for example. But also, we need to provide a way for those rules to become more and more lenient over time. It can be better to have a match that is not well-balanced than not having a match at all. So, operating a live service that is a critical part of the multiplayer experience is hard. If a game relies on matchmaking to allow players to play, this needs to be running like 24/7. We also need to keep in mind that games can have different life cycles. There are games that are in development, highly anticipated games with high CCU at launch times, viral games that have like a low traffic at launch and sudden spikes in traffic, and even daily variations in current concurrent users that have like resource requirement different depending on the time of the day. So the question is, when is the right time to invest into making a matchmaking service? Is it even worth it? How to figure what are the right resources to cater for those different scenarios? So now that we have exposed some of the problematic around how complicated it is to build a matchmaker, let's take a look at how Unity aims at solving those issues. So first, we're going to see how we're providing tools for game developers so that they can dynamically segment their player population and adapt to population variations. Then we're going to review how game developers can customize their matchmaking configurations to tailor it to their needs. And then how we allow to group players together based on their connection quality, that's quality of service integration. And then how do we handle sustained high throughput of tickets as well as spikes in ticket influx. So Unity's Matchmaker allows for different ways to segment player populations. First of all, queues. They support game-driven segmentation of population like game mode, 1v1, quick match, ranked, etc. Players from different queues will never be matched together. Then we have, for each queues are divided into pools. Pools are a dynamic segmentation of player populations that is using attributes that are defined on the matchmaking ticket. They are allowed to segment players based on the game version, their rank, or if they are cheaters, for example. Pools are a much blurrier segmentation, as we're going to see. Players from different pools could potentially end up being matched together, as the opposite of queues. I'm going to show some example of our UI. This is the Unity dashboard. Here we're seeing the matchmaker that's configured with 2 different queues, the quick match that we were talking about, and the ranked. And we can see like the quick match has 4 pools configured. Then let's look at the pool configuration of the queue. Here we can see that pools are configured in the context where game developers would like to support multiple incompatible versions of a game as well as a cheater island. Each pool has a set of filters that are defined to figure out in which pool a ticket should end up. Pools also have an order that has an impact on how players are being distributed in the different pools. So here are 4 different pools that support a beta version of a game, the official version of the game, and for each version, a cheater island. To determine in which pool a ticket is supposed to end up, Matchmaker will look at the attribute of the ticket, and then look at the first pool of the queue and check if the attributes fit the filters. If not, it moves to the next pool. The last pool don't have any filters to ensure that tickets that don't match any attributes eventually fails into a pool anyway. So now, this is the final set of the ticket distribution in the pool based on the different attributes and filters. We can see player C in the one beta cheater, player B in the no cheater, and then A and D in the 1-0 no cheaters as well. So now what's happening here is that we're realizing, the game developer realizing that they probably don't have enough players in the pool of this beta version, and the time to match is actually really high, and the player experience is not so great. To fix that, the game developer decided to disable the cheater island for the beta version of the game. The result is that the same ticket will be distributed differently. Player B and C will now end up in the same pool, bringing 2 smaller populations together, increasing the chance to find a match. So what about the configuration of a pool? With custom matchmaking rule engine, we allow game developers to define the composition of the match. What is the right number of teams? What is the right number of players? It also allows for more advanced matchmaking rule, like we were talking about earlier, like everyone has a different character in a team. This rule engine also supports relaxation over time of those rules, allowing to reduce time to match when the player population is lower. This is an example of a configuration for a match requiring 20 teams of 3 players to start a match. It's pretty simple and straightforward configuration. It's JSON, very easy to understand if you're used to read JSON. Here is an example of something a bit more complex that uses the example I was taking earlier. The match is made of 30 teams of 3 players. Each team members must have chosen a different character, and everyone in the match must have chosen to play on the same map. But the thing is that this is a quite restrictive configuration, right? And we may not be able to find 90 players to start a game fast enough. So we're going to allow to relax the minimum number of teams to start a game to 20 teams after 15 seconds, allowing for a match to start even though if it is not full. Also, if you don't like to play with JSON files, we have a pretty nice UI that's just like a quick example that allows game developers to modify the matchmaking rules without having to use JSON at all. Next, quality of service. How do we allow to match players together into the same region? Matchmaker integrates support quality of service that is integrated with game server hosting. This allows for game developers to enforce that players who are matched together have an equivalent connection quality. Because different games have different needs, it is possible to configure rules based on latency, packet loss percentage, or even both. But the player population can be lower in a specific region of the world, so we may want to be able to eventually to mix player population together. So like any rules, cross rules can relax over time to reduce time to match. Here's an example of what this looks like if a game developer would want to enforce all the players in a match to have a difference of latency of 30, eventually relaxing over time after 15 seconds to a difference of latency for 100. Scalable infrastructure. How to make sure that we have the right resources to handle the fluctuation of traffic. First of all, matchmaking service is backed by Google Kubernetes Engine from the Google Cloud Platform. This technology allows almost unlimited scale-up in the cloud to support extremely high traffic. Then there is virtually no cost for pools that don't receive any tickets, so we do not create resources for those pools. Finally, the Matchmaker architecture is built to support spikes in traffic while the service scales up. So now, let's dig into the architecture that allows for the scalability that we're looking with the Unity Matchmaker. How are we supporting queues and pools and the cardinality they could create? Game developers can have today 10 queues in each environment, and each queue can have 10 pools. That's a potential of 100 pools in total in each environment. We took the approach of if a pool is not receiving any tickets, we will not spend any resources for that pool. That's what we call scale to zero. There is virtually no cost for a pool that does not receive any matchmaking ticket. That enables us to rationalize our cost while still allowing for wide customization on the matchmaker. So before we move on, I want to introduce some concepts that we're going to talk about in the next few slides. We're going to talk about what is a ticket bucket. A ticket bucket is a combination of a project ID, and the environment is targeting, development, production, staging, the name of the queue, and the name of the pool. A ticket will always belong to a bucket. Then match process. A bucket needs a process to run in order for its ticket to be matched with each other. There is a one-to-one mapping between a bucket and a process, and a process can only match tickets of a given bucket. A process will also need we also need the matchmaking configuration defined by the game developers to understand how to group players together. And finally, a match process host. A match process host is basically a Kubernetes pod that executes one or several match processes, as we're going to see. So, scale to zero. Initial state. Let's start with the initial state. No processes are running. No match processors are scheduled. Matchmaker will schedule required resources to process matchmaking tickets on demand, as we just talked about. Our world map, right here, will keep track of those resources in order to know if a pool of tickets already has a process running. So first, a ticket comes in created by a player. We determine that this ticket will fall in the bucket 1. Matchmaker informs the world map that a ticket for the bucket 1 has arrived. No processes are running for that bucket, and also no match host exists either. So the world map will create a match process host record and assign the process for the new bucket to that host. When the match process host record is created on the world map, Matchmaker takes care of scheduling a new match process host deployment. And when the host starts, it creates the world map about the processes that it's supposed to run and then fetch the matchmaking configuration for that process. The configuration contains, between other things, the matchmaking rules. Once the match process is ready to match tickets, all the tickets for bucket 1 are forwarded to the host that is running the bucket 1 process. Next step, bucket 2 shows up. A ticket for bucket 2 shows up. No process is running for that bucket either, but there is a host available with some available process space. So the world map will just go ahead and add that process on the already existing host. World map informs the host that it is now supposed to run a new process for bucket 2. The match process host fetch the configuration again for that bucket and start executing the matchmaking process. And then, just as before, all the tickets for bucket 2 are now forwarded to the host. After some time, we end up in a situation where multiple hosts are running with multiple processes, and the world map is used to know how to route the ticket to the right destination. Now, bucket 1 did not receive tickets for a little while. That means that we can save resources by removing it. World map will remove the process from the host and inform the host that it should stop running it, effectively allowing for a new process to be scheduled on that host. If after some time a host doesn't have any process running, the host itself will be removed. So here's a high-level overview of our architecture. We have purposely removed some components that are more generic to keep the most important part of the matchmaking service. First of all, the tickets are received from the game client on the front end that saves them on our ticket DB. Those tickets are sent into a queue that we allow them to process them asynchronously. The front end also sends ticket signal to the control plane. The control plane is a service that will look into the world map to determine if a process is already running or if we need to schedule a new process. Then, when a process is scheduled, the match host is informed, like we just talked about earlier. 5, ticket routing worker act as a buffer between our front end and our match process, and then make sure that tickets are making it to the right destination. They use the warm up to understand when to send a ticket. Once tickets are matched together, the matches created are sent to the match workers, what we call the match workers, that are responsible for requesting server allocation and putting for the status of the server allocation. And once the server is allocated, Matchmaker assigns tickets with the server information. So how are we leveraging Google Cloud Platform and Google Kubernetes Engine to build the service and the architecture I just described? Here is a high-level architecture of our GKE deployment. Matchmaker is a Kubernetes native service. It uses Kubernetes API to schedule a match process host. It is made of 6 stateless deployments for them on a critical path that can scale horizontally based on traffic. 2 stateful sets for our ticket database and our warm-up. We also use PubSub for asynchronous workload, like routing tickets, request of server allocation, and this makes sure that messages are always delivered and also act as a buffer when the services are scaling up. We're also using different managed databases like Memory Store and Firestore for configuration and these kind of things. And finally, we use Dataflow, which they're basically listening to our PubSub topic and transform messages into metrics that are forwarded to our internal data pipeline that will then display them on the Matchmaker Unity dashboard. So the nice thing about Kubernetes application and GCP is that everything can be managed through code. Our infrastructure resources are created through Terraform. Services are created through Helm charts, and that makes deploying a new Matchmaker on GCP for development purposes very fast and reliable. This enables for a much faster development iteration. GKE allows us for a reliable and easy deployment of Matchmaker in our different development environment and staging environment, and this simplifies the different integration tests and helps us making sure that the integration of the different services we have are working as expected. This brings confidence in the changes we're pushing weekly to production, and we're also able to run very large testing early in development, validating the architecture of the Matchmaker. Some of the GKE key benefits that we are using today. The GKE high availability and reliability allows us to build a service with a very high overall uptime. The number of GKE nodes and the speed they scale out allows us to quickly react to spikes of traffic, as well as giving us the ability to sustain high throughput. And finally, the tooling like the managed properties and cloud logging enable us to track issues very easily. So, sorry, spoiler alert. GKE allowed us to scale out hundreds of nodes, allocating thousands of CPUs and hundreds of gigabytes of RAM for a full-scale testing that allowed us to validate the architecture of the Unity Matchmaker. So here are some of the results we got. Keep in mind that those are lab tests with a steady influx of tickets that will always find a ticket to match with, which is not the real life. That's a total of 153 million concurrent users who are playing 20-minute games. That's more than the Steam platform today. Technically, with more buckets, this number could also be increased, but we figured that was not necessary. We ended up the test here. We were quite happy. 3.3 seconds time to match for the 95th percentile, and 1.5 seconds for the 50th percentile. Sorry. What's next? What's next for Matchmaker? So coming soon, we have our Matchmaker CLI and configures files to configure much more easily our Matchmaker. If you don't like the UI, if you want to include your config as code in part of your CI/CD pipeline, This is coming. We're decoupling Matchmaker from game server hosting to allow matchmaking into a lobby and using the Unity relay. Matchmaker A/B testing allows you to do experimentation on your matchmaking rules, on your hosting, this kind of things. Matchmaker archetype-based templates, as well as later this year, Matchmaker into like third-party hosting support, peer-to-peer and dedicated game server, and match result analytics and reporting. That's it. Thank you so much.
Yeah, let's keep it going. Thank you so much. This was such an amazing talk. Isn't it amazing to see how, it's always humbling to see how our customers and partners use the capabilities of the Google Kubernetes Engine platform to accomplish such amazing things. So once again, a big round of applause. Thank you so much for sharing with us. I think we have a couple minutes for questions. There's a microphone back there. Anyone wants to come up, ask any questions? This is your chance.
Yes, I can have a small question. I'm interested in how flexible your filtering system. The deal is the game can be competitive and can be cooperative.
Sorry, I'm not sure I understood very well the question.
Sorry. Do you hear me?
Yeah, go ahead.
Okay, so I want to make the game, so I don't know. I like Led Zeppelin and beer, and I want to find the buddy to play with me. So the game is cooperative, not competitive. How flexible your rule system?
How is flexible our host system is?
Yeah, filtering.
So basically, like Multiplay, which is our game server hosting system, is support like any kind of servers, right? So it can run like Unity game server, it can run like Go servers, it run like any kind of servers that you want, any kind of executable you want to run on a server, basically.
So can I connect your filtering system to my database and to my rules?
Sorry?
Can I connect your filter system to my database and to my rule base? To totally external server?
So if your question is to host using matchmaking to use your own server, that's something that eventually that's going to come up later this year.
No, I have very tricky rules to combine the people together. So, and I want to use my system to create the rules and filters for this one.
Okay, I understand. Sorry.
Yep.
Okay. Yeah. So
sorry.
So we don't support custom rules today. And that's not something that we have really on the roadmap right now. So we will have to use like our custom rules engine to do like this kind of things.
Okay.
I'll be very curious to hear what kind of use case you have, so we can see. Maybe we can already do it with our custom engine.
Okay. Thank you.
Mm-hmm.
Any more questions?
So you mentioned that it was Kubernetes native, but is that support for GKE Autopilot or just regular?
No. So that's Kubernetes native in the sense that we are using Kubernetes APIs to run the matchmaker. So we create on demand, we create resources, we create Kubernetes resources on demand. It's not something that you can take and put into your own deployment or into your own cluster, right?
Okay, I see. So the infrastructure is all under the hood. As a client of Unity gaming services, we have no access to the infrastructure.
No, exactly. Yeah, you would have to use our SDK and our APIs to be able to create matchmaking tickets and get the matchmaking results. Yes.
Okay, thanks.
Mm-hmm.
One more question.
In one of your slides, you had the relay coming soon. Do you have an approximate date for this, or a quarter, or something like this?
I think we're saying, let me go back quick. We are saying Q2.
Okay, cool, thanks.
A question to maybe both of you. So going forward, because costs are important, especially if you go scale, do you have any idea, I know this is really hard to answer because it might depend on some internal decisions, but cost-wise, going forward, do you think there's going to be any optimization in either the way you set up, the way you run things, or so on, or billing, or how is pricing going to change maybe going forward, if going to change?
So on our side, what we're looking at is like we're looking at optimizing our workload and especially the match process workload. So we're trying to look at, okay, what kind of CPU do we need for our match processors to be running, and how much RAM do we need to do that? And we're looking at different sizes depending on how complex the matchmaking logic process is, depending on the rules and depending on the time it takes to iterate over a bucket of tickets. And that's something that we're looking to optimize the costs of our matchmaker mostly.
Okay, so you're still, because the question was more like, you're still looking into this, right? It's still going to get better. You're still going to try to improve this, right?
Yes.
Cool, thanks.
Mm-hmm.
Anyone else? I think that should be it. That should be a wrap. Thank you so much.
Thank you.
Once again.
Thank you, Brian.
Really appreciate it.